Hello and welcome to the final session of this course. This is a strictly review only session. No new material. We'll do 2 slides of review, then a example proof from Walter Rudin's book and some review Q&A. And that will finish up this course. And this slide is a summary of identity and inverse elements. There is no new material here, but in each case I've listed the function definition along with the identity element. The inverse element, if it exists, an NA with an asterisk indicates that the inverse element exists on a subset, in which case the subset is shown in the last column. And otherwise the set in the last column is the entire set the inverse and identity are valid on. So if there's a subset here, it applies to the inverse element. And you can see everything here is divided into 2 sections. One based on the definitions of addition, and the second part, the definitions of multiplication that we have seen. In this slide, I summarize many of the identity axioms that we covered. There's again no new material here. So these are axioms coming from the definition of the operation, properties of the operation, and identity elements as well as idempotence. Now, I've put everything here in terms of the AND operation or the intersection. You can swap the AND with an OR, and at the same time swap any 1 with a 0 to get what's called the dual equation, and you'll get the summation or the OR equivalent of what you see here. We haven't covered duals in this course. Just know that you can do this here. It's to save space on this page. In case of sets, you would swap union with intersection and empty set with the universal set to get the dual equation. Don't worry exactly about what the dual means, just know you can do that here, and I've done it only to save space on this slide. Again, no new material here, this has all been covered in the lecture sessions. And now we finally get to the example proof I've been promising. So this is Walter Rudin's example 1.15c, chapter 1 of his first edition of Principles of Mathematical Analysis. So he says that with elements x and y in the field of real numbers, prove that when x does not equal 0 and the product xy equals 1, that x is the inverse of y, or y is the inverse of x equivalently. So it seems obvious that this is true, but we have to prove it now using the axioms of a field. So let's start with the equation y equals y. We can't argue y equals y. Now we substitute for y the multiplicative identity. And we remember multiplicative identity, y times 1 equals y. That's the multiplicative identity. So I can substitute y times 1 anytime I see a y. So that's what's done in the second line. Now we recognize that we can rewrite the number 1, the rightmost number 1, as the multiplicative inverse. We remember from the definition of the multiplicative inverse, and remember the field has an inverse for each element, that x times the inverse of x equals 1. So we're simply substituting for 1 x times x minus 1 in the right parentheses. Now on the fourth line, we use the associative property to do the y times x first. So we have now y equals, in parentheses, y times x times the inverse of x. Now we substitute in, so we have in parentheses now y times x, or just yx. Now we're substituting in what we were given. So in the proof, at the very top, the actual proof that we're asked to solve, we're given that xy equals 1. So we substitute y times x equals 1 there, and we end up with the second to last line, y equals 1 times the inverse of x, and then again we have the identity element here because any element, inverse or not, times the multiplicative identity multiplied by the multiplicative identity yields that element back. So we've proven now that y equals the inverse of x using the axioms of a field. Now on this slide I've got a few more questions that test some of the material that I've gone over. So what you may want to do is read these and pause the video for a minute and try to think of the answers before I move on to the next slide where I'll give the answers. So first question, what's the cardinality of the set shown there inside the vertical bars? Remember, the vertical bars are cardinality. Second question, if the universal set is the set with the elements 1 and 2, the numbers 1 and 2 in it, what is the cardinality of the complement of the empty set, and what is the power set of the universal set S here? Third question, what kind of structures are the structure of natural numbers with the addition operation on natural numbers and the set of whole numbers with the addition operation? The fourth, y is the structure, the set of whole numbers along with addition and multiplication, a ring but not a field. And the last question, what is the answer? What is the result of, in parentheses, A intersection B union, in parentheses, A intersection the complement of B? And I'll give you a hint, think of set difference on that one. You may want to pause here for a second. In the last slide will be the answers to these questions. I have to rush this answer. I'm limited to exactly 2 hours on this course. So the cardinality here is just the number of objects in the set. It doesn't matter if they're nested or not. There's just 2 in number 1. If S, the universal set, has the elements 1 and 2, then 2 to the S has 4 elements as shown. And the cardinality of the complement of the empty set is going to have, that's going to equal the universal set, and its cardinality would be 4. Now, n, the natural numbers with the addition operation is a commutative monoid, while the same thing on the addition on the whole numbers is a abelian group because the latter has inverse elements and the first does not. There are no negative numbers in the set of natural numbers. And 4 is the case, y is whole numbers with addition and multiplication ring but not a field, and that is because the second operation minus the 0 element is not a group on the whole numbers because there are no numbers 1 over x in there. And last question, the answer is A here, and it's because the first term we end up with the intersection AB are the elements in A that are in B, and the second term ends up being the set difference A minus B, so those are the elements of A that are not in B. So the union of the elements of A that are in B and the elements of A that are not in B is the set A. And that concludes this course.